Oh, hi there. Didn't hear you come in. Welcome back, data management class. Hope you enjoyed the Lego display here. Lego's very popular in our house. We're going to look at some questions in probability. We're going to start with finding the probability that two or more people share the same birthday in a class. Then we're going to look at the probability of some other poker hands, more difficult ones. And then finally at the end, we're going to look at a special problem in probability. We're going to look at two of them. One will have to do with the probability that you guess on a multiple choice quiz and actually pass the quiz. And the last problem will have to do with Lego. So say you get a Lego set. This is the Heartland City Resort. Can't wait to build this. What is the probability, or what kind of, if we think about buying a lot of different Lego sets, what's the probability that a Lego set's missing a piece or pieces? I've heard that that does happen. It's not very common, and you can phone Lego and they will send the piece in the mail for you. But we're going to look at that problem and find that it's actually very similar to the multiple choice quiz problem as well. So there's really four examples we're going to work through. Now, one thing that these examples do have all in common is that although they don't have any new concepts, I think they're questions you probably wouldn't be able to do without help from me getting started. So come on, let's take a look. Let's take a look at our first interesting probability problem, and that's the probability of people sharing a birthday. In particular, suppose we're to choose 4 random students from the school. And what's the probability that at least 2 of the students would share a birthday? Well, I think the at least part should give you a hint here. Let's not break this up into cases where, we have to worry about whether 2 or 3 or all 4 of the students share a birthday. Let's use the complement, and let's actually look at the probability that none of them share the same birthday. And then we can just subtract from 100% to find the probability that at least 2 of them share a birthday. So how do we do this? This is fairly challenging to get started. But one trick is to actually think about these people's birthdays as being like a word of length 4, where each word, or each letter in the word, pardon me, is a birth date. You could think about April 28th as being a possibility for the first one, May 17th as being a possibility for the second one, May 17th might also be a possibility for the third, December 18th might be the fourth, and so on. So the total number, our outcomes now are basically like how many ways can we put these birthdays in order. That's 365 choices for the first birthday, and 365 for the second, 365 for the third, and 365 for the fourth. So multiplying those those numbers together gives us there are 365 to the power of 4 possible ways these 4 students could have birthdays. Now, what's the probability that they're all different birthdays? Well, that means we have 365 possibilities for the first person's birthday times, well, the second person's birthday can no longer be whatever birthday was chosen here. So if it was April 28th, it can't be April 28th. So we only have 364 choices. Continuing on, we have 363 choices for the third birthday and 362 for the fourth. So that's the probability that none of them share the same birthday. Now, one way to figure that out is just punch that all in on your calculator, and you can do it, and you get about 0.9836. So a 98.4% chance that they don't share the same birthday. I would like to point out that this calculation in the numerator, that's really the number of permutations from 365 that have length 4, or 365p4, the number of permutations of length 4 we can get from 365 different symbols. And in this case, our symbols are the dates, the birth dates. Now, we technically haven't answered the question yet. 1 subtract 0.9836 gives us 0.0164. Or there's only a 1.64% chance that any of these 4 students share the same birthday. Now, a little more interesting might be, how about a class of 23 students? Now, what is the probability that two students, at least two students, share a birthday? So we can use the exact same reasoning, just the numbers are way bigger. So now there are 365 to the power of 23 different possibilities. So our length 4 here, string or word, is now 23, length 23. And up here, now we look at all the, assuming they all have different birthdays, we have 365 possible birth dates for the first person, 364 for the second, all the way down to the last person, who there are now 343 possible birthdays left. Now again, that's just the same as doing the number of permutations of length 23 from 365 characters, or 365p23 is a much quicker way of doing that on your calculator than multiplying those 23 numbers together. If you do that, you'll find you get about 0.4927. That's the complement. That's no one sharing the same birthday. So the real probability that we're looking for, we get by subtracting. So that's about 50.7%. So in a class of 23 people, it's actually slightly more likely that two students would share a birthday than not, which I think is kind of interesting. Most people think that that's, kind of a big deal if someone in their class, if two people in a class share a birthday, but as it turns out, it's actually not that surprising at all. Let's try our next example. It's going to involve poker hands again, but this one's quite a bit more difficult. So just bear with me and relax. I'm walking you through some examples that I don't think you would get on your own, including the birthday problem, and this next one's maybe even a bit trickier. Let's look at the probability of being dealt 5 cards, and they're all the exact same suit. All hearts, all spades, all clubs, all diamonds. Okay, here's an example of a flush, all hearts. Now, of course, the order you get cards in does not matter in poker. So if we look at all the possible hands in poker, that's 52, choose 5. We've talked about that quite a few times. The number of ways you can select 5 cards out of 52. Now, how many of those will be flushes? Well, one way of doing it is to say, look, there are 4 suits, choose one of them. Or just the number 4 is fine there, because 4 choose 1 is 4. Once you've decided, say, for example, hearts is going to be your suit of choice, or whatever it might be, then there are 13 hearts in the deck, and you need 5 of them. So 13 choose 5 is the number of ways you can pick 5 hearts out of 13 total hearts in the deck. Multiply that by the 4 different suits you could have, or 4 choose 1. If you do that, I believe you get 5,148 out of 52 choose 5 is 2,598,960. And that is very close to 0.2%. It's a very low probability. It's not too likely. Now, there is another way to do this, and I'm pretty sure you've seen this strategy too, and that's that we can choose to do this using events, basically. There is, let's start by assuming that you want to flush all hearts. The probability of getting all hearts can be calculated pretty easily. There are 13 out of 52 cards that are hearts. That's your first card you get. Times, you need a heart on the second card, and there's only 12 of them hearts left out of 51 cards, and then we just keep going. The third card, then we move to the fourth card, and the fifth card. When you get to the fifth card, there's only 9 hearts left out of 48 cards total. Now, that's the probability of getting 5 hearts dealt in a row. We multiply the probability of each event happening. However, we technically need to times that probability by 4, because that you could also have all diamonds, all spades, all clubs. That'll give you the exact same answer. Very, very different approach, but both are correct. This one uses combinations. I think of this one as using like events. Now, the reason you're able to do that with a flush is because you need to get a heart or a diamond or a club every single time. So it's pretty easy to break it down into this strategy right here. That's not true with the next example. What is the probability that you get 3 of a kind
So 3 cards, all the same rank. The example given has 3 aces, but it could just as easily be 3 kings or 3 tens or 3 twos or whatever else. That's more complicated because 2 of the cards can be whatever. The other 3 have to be the same, and then the order that you get them in doesn't matter. So there's lots of possibilities. Let's take a look at this probability together. So 52 choose 5 is still our total number of outcomes. So the way I think about it is like this. There are 13 possible cards that we could have to make a 3 of a kind with. It could be aces, twos, threes, fours, all the way up to kings. That's 13. So in a way, I think of that as 13 choose 1. The number of ways you can pick the rank that is going to make your 3 of a kind up. Once you have that, you need 3 of those cards. There are 4 aces in the deck. So there are 4 choose 3 ways of deciding which 3 aces you'd have, or which 3 tens, or which 3 kings, or so on. Finally, you have 2 other cards, and you don't care what they are. I could make another 3 of a kind in this example on the page by replacing the king and the 10 with the jack of diamonds and the queen of hearts, or whatever I want. There are 48 cards left. Choose 2 of them. If you figure that out, you'll find this probability is about 2.26%. If you're thinking to yourself, oh, actually, I think there's something wrong with that, just hold on one second. I'm going to come back to it. There's nothing wrong with it, but we'll do the next question and then we'll revisit this one. What's the probability you're dealt a full house? That's actually a slightly easier question. A full house is a pair and a 3 of a kind. Okay, it's a harder hand to get than a 3 of a kind, but the probability is actually easier to calculate. 52 choose 5 possible poker hands. Okay, now I got to think about it this way. Let's start with the 3 of a kind. That's very similar to what we saw up here. We can do 13 choose 1, or just 13. 13 choose 1 is 13, times 4 choose 3. The number of ways I can make a 3 of a kind. 3 threes, 3 fours, 3 fives. That's all the possibilities. But now your other 2 cards must be the same rank. And there are 12 possible ranks left. We actually can write 12 choose 1. So I've picked my 3, I've chosen my 3 of a kind using 13 choose 1, so threes or fours or whatever else. There are 12 ranks left that I can pick to make my pair with, and there are 4 choose 2 ways to make a 2 of a kind from that rank. So 12 choose 1, maybe I have queens is what comes up for that, and there are 4 choose 2 ways to come up with 2 queens out of the 4 queens in the deck. So queen of diamonds, queen of clubs is one, queen of clubs and queen of hearts is another, queen of hearts and queen of spades is another, and so on. There's 4 choose 2. That's actually only 6 possibilities. Now if this 12 is giving you a hard time, that's because, look, I can't, once I've got my threes as my 3 of a kind, I can't have a pair that's 3. So there's only 12 possible ranks left because 3 is no longer a possibility. If you figure all that out, I believe you should get about 0.144%. So it is very unlikely that 5 cards dealt to you will end up being a full house. Now, if you look at this example here again, the probability of 3 of a kind. Technically, in this example, we've included all the full houses. We've said a full house is still a 3 of a kind. Some people might say, no, take the 2.26% and then subtract this amount so that the full houses aren't included as part of the 3 of a kind. It doesn't really matter, and there are other ways to do this calculation that don't include the full house, but I'm okay with that right now. Okay, so this one's a difficult one, and you might need to revisit this again. I'm going to give you some other card hands to figure out, and you can use this video to kind of help you with that too. The next thing we're going to move on to is a very special problem in probability. There are a number of problems that are the exact same as this one right here, and this is going to set up our next unit on what's called probability distribution. So pay attention, maybe read through this, and let's get ready to answer this question together. I'm sure all of you have done a multiple choice quiz before, and probably many of you have thought about what it would be like to guess all of the answers. So in this question, let's suppose a multiple choice quiz has 4 possible answers, A, B, C, D, and 20 questions on the quiz in total. And suppose for the sake of this question that you randomly guess the answer to each question. I don't know how you come up with a random guess, but you do that somehow. What's the probability of guessing the correct answer? Well, there's 4 possibilities, so 1 out of 4, or 0.25. The incorrect answer would happen 3/4 of the time, or 0.75. So there's our 2 probabilities. Probability of success and failure on one question. How many questions would you expect to get correct? Well, most people don't have too much of a problem with this idea, that we would kind of expect that 25% of the 20 questions would be correct, which gives us 5. And that is what's called the expected value. One way of thinking about that is if everyone in the whole world did this activity where they guessed on the 20 questions, we would expect the average score to be 5. If everyone in our class did it, okay, maybe the average score wouldn't be 5. It could be higher or lower because we might get lucky or unlucky. But that's what we would expect to see for an average. We can figure out some probabilities. How about the probability that you get a mark of 0 on the quiz? Well, let's look at this right now. We can treat each of the 20 questions as if they're events, and they are independent events. The probability that you guessed correct on the first question shouldn't change the probability that you guessed correct on the second question, assuming you're actually guessing, you're not even reading these questions. Well, we can multiply probabilities together then. Probability that you get the first one wrong and the second one wrong is 0.75 times 0.75. Continue that for all 20 questions, and 0.75 to the power of 20 is the probability that you get all 20 questions incorrect. 0.75 to the power of 20 is approximately 0.317, and that is a percent, not a decimal. So it's very unlikely you would actually guess and get no questions correct. Okay, well, what's the probability that you get exactly 1 out of 20 on the quiz? Exactly 1 question correct. And that's quite a bit more difficult. One way to do it is you might say, okay, well, there's a 25% chance that I get the first question correct. Well, I'll multiply that. I want exactly 1 out of 20, so it means I do need to get all the remaining 19 questions incorrect. Now, that probability right there is very small. That's actually the probability that you get the first question correct and the last 19 incorrect. Well, that's not the only way to get 1 out of 20 on the quiz. You might get the second question correct and the rest incorrect, or the third question correct and the rest incorrect. Those would all work out to the same number, but there's 20 cases, all of the same. I can multiply by 20. So that's the probability I get the first one correct and the rest wrong, and then I multiply by 20 because there are 20 possibilities for the question that I might get correct. That's quite a bit more likely, actually. It's about 2.1%. If you type that in, that's what you should get. Well, what's the probability that you get exactly 5 correct answers on the quiz? Well, let's assume that the 5 correct answers are the first five questions. And from there, so the probability to get the first 5 correct times the probability you get the last 15 incorrect. So that's one way that you might end up getting exactly 5 correct answers. You got the first 5 right and the next 15 all wrong. But there are lots of ways that you could do it. I mean, imagine all the ways you could get, there are 3, 4, 5, and then a bunch wrong. You could also have the first one right, the second one wrong, the next 2 right, the next 2 wrong, and then a right, and the rest wrong. There are lots of ways that you could choose 5 questions to get correct. So actually we multiply by 20, choose 5. let's just go through this again too. This is an important probability question and an important question. 0.25 to the power of 5 times 0.75 to the power of 15 is the probability of getting the first 5 questions correct, and the probability of getting the last 15 incorrect, then multiply by 20, choose 5 for the number of ways you can choose 5 out of 20 questions to get correct. In our other example, that was simpler, because here we just multiplied by 20, because we said there are 20 ways to pick the one question that you might get correct. In fact, we might have used 20 choose 1 instead of just 20. However, there are way more possibilities here because there are 20 choose 5 questions that I want to get correct. If you figure that out, you get 0.202 or 20.2%. So that's not an unlikely outcome at all. And that shouldn't be surprising because 5 was the expected number, what you would expect to happen. But just because it's the expected amount, it doesn't mean that that is the, it's not a probability of over 50%. Okay, it's still only 20%. It's still more likely that you're going to be lucky or unlucky and have some other number other than 5 correct. I can guarantee you, though, that that would be the highest probability. If we went ahead and calculated the probability of getting 6 correct or 7 correct, you'd find that those probabilities are lower than 20%. And then, of course, comes the big question here. What's the probability that you pass the quiz? That is a much more complicated question because there are lots of ways to pass the quiz. You could get 10 correct. I guess that's the most likely way. You get exactly 50% on the quiz. Well, what's the probability that happens? 0.25 to the power of, let's see, 10. And then you get, say, the last 10 incorrect, so 0.75 to the power of 10, times 20, choose 10. That's one possible way that you could pass the quiz, but you also might get 11 correct. That would be 0.25 to the power of 11 times 0.75 to the power of 9 times 20, choose 11. So in this example, saying 11 correct, imagine I got the first 11 correct, followed by the last 9 incorrect, times 20, choose 11, because there's 20, choose 11 ways to decide which 11 questions you get correct. You would have to add all these probabilities up until you finally get to the probability of getting perfect. Now, the probability of getting perfect is ridiculously small. It's 0.25 to the power of 20, which is a number that barely registers on a calculator. It's so small. I mean, it registers, but it's just barely changes the answer. So for fun, I went through and I did all the possibilities. I actually used Excel to do this. I did some fancy formulas, some copy downs, and there you can see all the probabilities here. Notice the probability of getting 10 correct is still very, very small. For my final probability as a decimal, there's about 1.4%. So there you go. You have actually about a 1.4% chance that you would guess on this quiz and pass. So I guess it's possible. It's a bigger probability that you pass than you'd get 0 out of 20. This also might be why it's a good idea in multiple choice quizzes to have 5 answers instead of 4, because that number goes down drastically if you change to 5 possibilities instead of 4. Okay, we've got one more problem to look at. Let's go to that now. On to the Lego sets. Suppose that Lego manufacturers want to concern itself with quality control. How many Lego sets will be missing pieces or have some be packaged incorrectly or something like that? And suppose Lego has concluded that 99% of its sets are packaged correctly. They're not missing a piece or anything like that. And let's assume that 1,000 Lego sets are shipped to one store. And we're going to look at probabilities of how many Lego sets would we expect to be packaged incorrectly. And we're going to find out this is exactly the same problem as guessing on a multiple choice quiz. By the way, that 99.7%, I'm just making that number up. I really have no idea. So what's the probability that none have been packaged incorrectly? So if they're packaged correctly 99.7% of the time, it means 0.3% of the time they're packaged incorrectly, or 0.003. So what's the probability that none have been packaged incorrectly would be 0.997 to the power of 1,000. Okay, it's the probability the first one is correct times the probability the second one is correct, and so on. That's about 4.96%. So it's possible, but actually a little bit unlikely that we wouldn't have at least one that had some issues. What's the probability that exactly 2 have been packaged incorrectly? Well, like the multiple choice quiz example, we could assume that the first 998 are packaged incorrectly, and the last are packaged correctly, pardon me, and the last 2 are packaged incorrectly. However, we can choose 2 of the 1,000 to be the defective ones. If you figure that out, you get 0.224 or 22.4% approximately. So that's a very likely outcome, somewhat likely. Now the 1,000 choose 2, because that's the number of ways you could pick the 2 incorrect Lego sets out of the 1,000. Notice you could have also done 1,000 choose 998, the number of ways to pick 998 Lego sets that are packaged correctly. And those are the same. 1,000 choose 2 is the same as 1,000 choose 998. Kind of like our Lotto 649 example, where Lotto 649 choose 6 winning numbers out of 49. Could be Lotto 4349, choose the 43 wrong numbers, if you remember that example. Finally, what is the probability that at less than 3 have been packaged incorrectly? Well, we already looked at the probability that 0 were incorrect. We got 4.96%. We then looked at the probability that exactly 2 were incorrect, and that's 22.4%. We did not look at the probability that exactly 1 was packaged incorrectly. So those are all the cases of less than 3. So let's just calculate the probability that exactly 1 is packaged incorrectly. That'd be 0.997. So the first 999 are fine, times 0.003 times 1,000 choose 1, or just 1,000. So the number of ways you could pick the 1 out of 1,000 that's packaged incorrectly. That's about 14.91%. So all we do to figure this out is take 14.91% plus 22.4% plus 4.96%, and we'll get an answer of about 42.27%. So there's a 42.27% chance that we'll have less than 3 issues out of the 1,000 Lego sets. You can maybe appreciate why this is an important question. I mean, besides how useful this is, it kind of tells us what we can expect to happen in this kind of situation. It also is the beginning of what's called probability distributions, and we're going to learn all about that in the next unit. It uses this idea to basically allow us to figure out how random certain things are. And this is an example of what's called a Bernoulli trial. Now, one thing I didn't mention that I should really address here is that for this Lego example, the assumption that we made is that these were independent events, which in all likelihood they're probably not. The multiple choice quiz for sure, guessing on question 1, guessing on question 2, those are independent events. But here they might not be. For example, if you say you own the store and the 1,000 Lego sets show up, and you find that the first one has a problem with it, the probability that the second one doesn't have a problem is probably not 99.7%. There's probably something wrong with the machine, or that particular day there might have been a problem. So these may not be independent events, but it's certainly okay to think of them as if they were. Okay, that's it for today. Bye for now.